Hey there, have you ever just stared at a graph, one with those smooth connected lines, and thought to yourself, how on earth am I supposed to describe all of that? I mean, it's literally an infinite number of points. Well, you are in exactly the right place. Today, we're going to master domain and range using a really simple, super powerful, and honestly, kind of fun method. So here's what we've got on tap. First, we'll talk about why going from simple dots to connected lines is such a big deal. Then, I'm going to introduce you to my secret weapon, the trash compactor method. After that, we'll jump right into some examples, point out a few common mistakes so you can avoid them, and finally, we'll see why any of this actually matters in the real world. All right, let's dive in. First things first, we're making a jump here from looking at graphs with just a few scattered points to graphs made of smooth connected lines and curves. And you know what? That one little change brings up a huge new challenge, the problem of infinity. No, really, think about it for a second. Between any 2 points on a line, no matter how close they are, you can always find another point, and another, and another. It goes on forever. There is no way, it's literally impossible, to sit down and list out every single coordinate. So, what do we do? Well, the solution really comes down to this big difference. With what we call discrete graphs, just a handful of separate dots, it's easy. You can just list the points. Done. But with continuous graphs, those smooth lines, we need a totally new tool to handle that whole infinity thing. And that tool is inequalities. They let us describe an entire chunk of the graph all at once. And here it is. This is the tool we need, but we're going to wrap it in a really easy-to-remember idea. I call it the trash compactor method. And I promise it's going to make finding domain and range feel super intuitive. First, let's get our terms straight. The domain is all about the x values, just the x's. The easiest way to think about it is this. How wide is the graph? What's its total horizontal spread, from the farthest left point to the farthest right? And then you've got the range. It's the exact same idea, but for the y values. It's all about the vertical. So you just ask yourself, how tall is the graph? What's its lowest point, and what's its highest point? Okay, here's how the method actually works. I want you to imagine that your graph is made of something squishy, like clay. To find the domain, picture two giant walls, one on the left and one on the right, closing in and squishing that graph completely flat against the x-axis. The little shadow or mark it leaves behind, that's your domain. And we always find it by scanning from left to right. Then, for the range, you do the same thing, but with a floor and a ceiling, squishing the graph onto the y-axis. And this is key. For the range, we always scan from the bottom to the top. All right, that's enough theory. Let's be real. The best way to get this is to actually see it work. So we're going to walk through 3 different examples, starting off easy and then adding in a few little twists. Let's kick things off with a simple, basic line segment. Now, the first thing you should always notice are the endpoints. See how they're both filled in solid circles? That's important. It's telling us that those points at the very end are included as part of our graph. Okay, time for the trash compactor. For the domain, our walls are squeezing in from the left and right. Where does the shadow on the x-axis start? Well, it starts at an x value of -2. And where does it end? At an x value of 3. Now, since both of those endpoints were solid, closed circles, we use the less than or equal to sign. So our domain is all the x values from -2 to 3, including them both. Now for the range. We squish the graph with a floor and a ceiling. Remember, we scan from bottom to top. The lowest the graph ever gets is a y value of -1. The highest it ever gets is a y value of 4. Again, those points are included, so we use the or equal to signs. Our range is -1 is less than or equal to y, which is less than or equal to 4. Easy as that. Okay, let's level up a little bit. What happens when one of those endpoints isn't actually part of the graph? That's exactly what an open circle means. It's like a boundary line. You can get super, super infinitely close to it, but you never actually touch it. Let's apply our rule. Scanning left to right for the domain, our shadow starts at x equals -3. But wait, that's an open circle. That means we don't actually include -3, so we have to use a strict less than sign. The shadow ends at x equals 2, which is a closed circle, so we do include that one, using less than or equal to. And that gives us our answer. -3 is less than x, which is less than or equal to 2. And we're going to use that exact same logic for the range, scanning from bottom to top. What's the lowest y value? It's -2, and that's part of the solid line, so we use less than or equal to. What's the highest y value? It's 3, but it's attached to that open circle, so we just use less than. And there's our range. Y is between -2 and 3, including the -2 but not the 3. Okay, for our last example, let's look at a graph that doesn't have endpoints at all. Instead, it has these arrows. Whenever you see arrows on a graph, it means that the graph just keeps on going forever and ever in that direction. In this case, we've got a parabola. Now, let's use our trash compactor on this one. For the domain, our walls try to squeeze it, but as this parabola goes up, it also gets wider and wider and wider forever. The walls would just have to keep moving apart. It's eventually going to cover every single possible x value on the number line. When that happens, we say the domain is all real numbers. But what about the range? That's a different story. Scanning from the bottom up, we can see the graph has a clear minimum point, a floor, right at y equals 0. And it actually touches that point, so it's included. From there, both arms of the parabola shoot up towards positive infinity. So our range is all y values that are greater than or equal to 0. Okay, so you've got the method down. Now, let's quickly talk about a couple of really common traps that students fall into. Seriously, if you can just remember to avoid these two things, you're going to be in great shape. This is the big one. Promise me you will always, always, always write your inequalities from the smallest number to the largest number. Just think of a number line. -2 comes before +3, right? So you have to write it as -2 is less than or equal to x, which is less than or equal to 3. Writing it the other way around is just confusing, and honestly, almost every teacher will mark it wrong. Small to big, always. The other thing that sometimes trips people up is the vertical line test. You probably remember that. But here's the thing. It's a completely different tool for a completely different job. The vertical line test checks if a graph is a function. It has absolutely nothing to do with finding the domain. Remember, for domain, we're squishing the graph horizontally to find its shadow, not scanning it with a vertical line. So why are we doing all this? I know, it can feel a little abstract in a math class, but domain and range are actually incredibly useful ideas for describing the limits and possibilities of all sorts of real-world systems. For example, picture an engineer designing a roller coaster. The domain for that roller coaster is the time the ride is actually running, let's say from 0 seconds to 120 seconds. The ride doesn't exist before it starts. And the range? That's the height of the track, from ground level all the way up to its tallest peak. Engineers absolutely need to know that range to make sure the ride is safe and the supports are strong enough. So the next time you see a graph out in the world, maybe it's tracking stock prices or the temperature for the day or even the speed of a car, take a second and think about it. What's its domain? What's its range? You have the tool now. You know how to find out.